Y's correlation coefficient, or R of xy, is a number always between y and -1. Recall that correlation coefficient is a measure of linear relationship between x and y, sort of recalled or reminded using these 6 scatter plot here. As you can see, x is a horizontal axis variable and y is a vertical axis variable. In these scatter plots, for example, first one, you see that the way that dots are scattered are in a way that the trend line turned out to be just a flat horizontal line indicating near zero linear relationship, or r equal to 0. In the next one, you can see that r is now -0.3, so it's a sort of weak negative relation between x and y, and you can see that there is a negative trend line, and the dots are widely scattered around the line. So that's the reason we are having a weak or closer to 0 correlation coefficient. With things getting more concentrated, r is getting to a higher value, but in this case is a positive trend line, so r equal to 0.5. And then again, with further concentration around the trend line, but in a negative fashion, we get to now r equal to -0.7, so approaching minimum value of -1. And then in a positive trend or fashion, with even further concentration around the line, but in a positive trend, we get r equal to 0.9, and finally, in near perfect negative relationship, basically dots are close to near perfect on the trend line. So r is now getting to almost -1. So what is the reason for this? Okay, just bear in mind that the correlation coefficient is, as usual, is a normalized version of covariance. So you can say covariance of x and y divide by standard deviation of x divide by standard deviation of y, and the reason we do that is because we are normalizing covariance. Another symbol for covariance is sxy divided by sxsy in terms of sample statistics. Just recall before I move on to quick proof. Proof is easy. In textbooks, you will see instead of rxy, people, for example, say rho xy. And then instead of sigma, instead of s or sxy or sx or sy, people start saying sigma xy, sigma x, and sigma y, as you can see here at the bottom of the page. This formula at the bottom of the page is the same concept, except it is for population statistics, not sample statistics. So when you're dealing with the whole population, then you use the formula at the bottom of the page, but it is the same concept. So let's stick with the sample statistic and correlation coefficient R. Okay, so as a quick proof, I'm going to start this. I can say sigma I from 1 to n is the sample size for the data set that you have. Let's say 30 people or 30 things. So I can say sigma a, and a is the constant, so a is a constant, let's say just not equal to 0, so non-zero constant. Constant can be a positive or negative number. It's a real number, so real number, but not non-zero real number. Okay, so assume that's the case, then I can write sigma I to n a times xi minus x bar, average of x, plus yi minus y bar, the whole thing here inside sigma to the power 2. So the whole thing inside sigma to the power 2. Because it's a summation of n number of things that are raised to the power 2, obviously the whole thing is greater than or equal to 0. So we know that. And it is no matter what a, so it is independent of a value as long as we are saying a is a, be careful, so as long as we are saying a is a non-zero real, it can be positive or negative, but non-zero real, then this holds. Okay, so what is the consequence of this? The consequence of this is, let's expand, so sigma I1 to n a squared xi minus x bar squared plus, I am raising to the power 2 and also distributing sigma. Sigma I1 to n 2 times a xi minus x bar yi minus y bar, and finally sigma I1 to n, and we have yi minus y bar squared. And this whole thing should be greater than or equal to 0. This is valid. So this whole thing should be greater than or equal to 0. Okay, so let's divide the whole thing by n minus 1. So I am going to divide this by n minus 1. I'm going to divide this by n minus 1. And I'm going to divide this by n minus 1. We know that n is a sample size that is greater than or equal to. So we can safely divide everything by n minus 1 without being worried that the denominator is 0. Usually sample size is considerably larger than 2, but you're saying minimum is 2. Now, the first term here is obviously a square s square, because if you take a square outside of the first term, it just becomes definition of a variance or a square root of a standard deviation. The second term here is the definition of 2a times, so take 2a outside. So you can take 2a outside just to sort of visualize it and put the sigma there. This whole thing here is the definition of the covariance. So it is the definition of basically 2a covariance of xy. And the last term here is obviously definition of variance of y, which is square root of a standard deviation of y. And we are saying this is greater than or equals 0. Okay, what do we need to do? It's as simple as this. So I am going to make do a little trick here. So let's keep it this way: 2a sxy, and next one that I'm going to play with is this trick. I'm going to say it is sxy squared divided by sx squared. So that's my trick. And as a result, since I added this component here, I need to subtract that component as well. So I added and subtracted the same thing as if I didn't do or add anything. There you go. Okay, what is this term here? What is this term here? This term is a very interesting term, actually. It's the expanded version of this. A times sx plus sxy, plus sxy divided by sx to the power 2, n plus sy squared minus sxy squared divided by sx squared to the whole thing greater than or equals 0. Now, okay, so this component here, the first term, is naturally a term that is always positive or at minimum 0. So that is obviously greater than or equals 0. Okay, the minimum value of this term is 0 when, if a is set to equal to, say for example, negative sxy divided by sx squared. If you do that, then the first term becomes, then first term is 0. What is the consequence of this? Well, we are saying this statement here, this whole thing here, we are saying this whole thing always, no matter what a is greater than or equals 0, including the case that the first term is 0. As a result, we get the fact that the second term should also be greater than or equals 0, including the scenario, for example, if you set when a equal to this term, that result the first guy to be exactly 0, then you need to have the second term greater than or equal to 0. So we get sy squared minus sxy squared divided by sx squared greater than or equals 0, which result in exactly what we wanted. Result in exactly what we wanted, which is the scenario that we said we get we get 1 should be greater than or equal sx squared divided by sx squared sy squared, which means exactly what we wanted. 1 is greater than or equal to absolute value of r squared, because as you can see, rxy is equal to sxy divided by sxsy. So this is exactly the proof we were looking for, this outcome. So it's a reminder that there is a very simple proof that we can show using this simple proof that the correlation coefficient has to be between 1 and -1 at absolute highest value. 1 indicate perfect correlation coefficient, and minimum absolute value of 0 indicate no linear relationship between x and y value involved. I hope that this example is helpful in terms of reminding and illustrating the different situations with respect to linear relationship between two statistical variables x and y, and this interesting simple proof.